Assignment 1.d, E, that is layout of CMOS 2 input NOR gate and CMOS 2 input OR gate. The transistor level schematic for NOR, OR gate is as in front of us. PMOS transistors P1 and P2 connected in series, while NMOS transistors N1 and N2 connected in parallel. P1, P2, N1 and N2 form the schematic for CMOS 2 input NOR gate, while transistors P3 and N3 form the basic CMOS inverter. As shown, the source of P1 is connected to VDD, drain of P1 connected to source of P2. The drain of P2 is connected to the interconnection of the drains of N1 and N2. Source of N1 and source of N2 are shorted together and connected to VSS. Gate of P1 connected to gate of N1 using polysilicon. Gate of P2 connected to gate of N2 using polysilicon. The output of NOR gate is labeled as Y NOR, and it is given to the input of CMOS inverter formed by P3 and N3. Output of NOR gate Y NOR is available on metal 1, while the input of CMOS inverter is available at polysilicon layer. So we must use a metal 1 to polysilicon contact as shown. Input A has frequency FA, while input B has a frequency FB, and FB is 2 times the frequency FA. Now we will convert this transistor level schematic into a layout in microwind. So as seen before, we can place one PMOS and one NMOS in the workspace, and we can copy those devices and replicate them. Select PMOS, generate device, select NMOS, generate device, reduce them, select copy elements, replicate them 2 times. Similarly, copy NMOS and replicate it 2 times. Now we will arrange them so that they look like our transistor level schematics. We can move this here. So understand, this is P1, P2, P3, N3, N1, N2. P1, P2, N1 and N2 should be connected suitably to form the 2 input NOR gate, while P3 and N3 should be connected suitably to form the CMOS inverter. Now as per the schematic, P1 and P2 are connected in series while N1 and N2 are connected in parallel. So we select stretch and move, place it here, we place it below. Similarly, we will place N1 and N2 so that they can be connected in parallel. Similarly, P3 and N3 are aligned properly so that they can form an inverter. Now we can zoom this, and we can bring this devices little bit nearer here. Place P1 and P2 sufficiently away from each other such that the distance between them is at least 11 lambda. For that we can use this measure distance tool. So it is approximate, it is less than 11 lambda. Yeah, so we can place them little further away. So let us measure the distance again. Now make the connections. Take metal one. You can align them properly. Source of N1 connected, drain of N1 connected to drain of N2. Drain of P2 connected to the intersection of the drains of N1 and N2. Connect the source of N1 and source of N2 together. Apply VDD. Apply ground. We must define the intersection of the drains of N1 and N2 as output node. Let this be named as Y NOR. Now we will construct the basic inverter. There is a malalignment, so we will say undo. Connect the gates. Apply VDD. Apply ground. Polarize all anvils. You can connect the gates of P1 and N1 together. Similarly, connect the gate of P2 to gate of N2. Now we can connect the output of NOR gate, the input of inverter, this way. Take metal one here. Take polysilicon, connect it here. Define the output of inverter as the output of OR gate. Apply the input A. Make its frequency 2.5 gigahertz. Take another clock. Apply it here. Rename it as B and make it 5 gigahertz. Perform a DRC, no design rule errors. Now you can simulate it. Remove all the checks. Click reset. Show less number of cycles. You can see here for inputs A equal to 0 0, the output of OR gate is 0, output of NOR gate is 1. For 0 1, output of NOR gate is 0, OR gate is 1. For 1 0, output of NOR gate is 0, output of OR gate is 1. And for 1 1, output of NOR gate is again 0 and output of OR gate is 1. So the waveforms for output of NOR gate and OR gate are matching exactly with the truth tables of a 2-input NOR gate and OR gate. We can save this layout as CMOS NOR OR.